we have the last session of this workshop with the last talk and the only one. And this will be the talk of Artem. Please.
Thank you. Thank you for this introduction. And so, yeah, first of all, I would like to thank the organizers for this workshop. It's been a pleasure. I learned very many new things, and yeah, so I'm happy to tell something new or like what I'm doing. So, all right. So like my title is is a bit I was a bit uncertain what to put inside. So I wanted to put something about spin impurity and temperature gradient, and but how accurate that is, let's decide on fly. And yeah, so like the talk is based on this paper with Rafael, Angela, and Nikolai. And please ask questions. So the slides are fairly new, and I'm not 100% sure that they are coherent enough. So if you have some questions, please interrupt me and let's decide what's going on. All right. And I would like to talk about temperature gradient. And I thought like a good way to start is to start with the Zebec effect. So that's a pretty standard thermoelectric effect that we know from textbooks. So like if you have a hot side, say, and cold side, and then you will have like a motion of carriers, electrons, and then you will have some current. All right, so that is very good. And like actually now we don't use, we do use this effect, but like 200 years ago, that was one of the like most stable ways to produce current. And I think that like Ohm apparently used this effect in his lab to show that his law was correct. And like the basic understanding of this effect is in a way quite classical, although it's based, of course, on quantum mechanics. So like you have some hot side, which has a bit larger average momentum or pressure, and then it pushes your electron to the cold side. And then like this motion, basically, due to the heat transfer, generates a charge current. And what is missing, like in this picture, is a spin. So basically, you know that electron is not just a charge carrier, but also a spin carrier. That is important. That's basically somehow important for this talk. So that's why I decided to emphasize it like on this slide. So here, that's an electron, and each has like spin. So of course, like it's a quantum mechanical, spin is a quantum mechanical property. So you can't just draw like that, but like for the purpose of this talk, I will always draw it like that. All right, and then like when we think that spin is important, then a natural question would be to ask, so you have charge current, and then you could also define a spin current. So that's basically say, yeah, like spin, it's a difference in the motion of spin ups and spin downs. And then the question would be, can you manipulate this current using temperature gradient in pretty much the same way, or like using the same idea that you had for the Zebec effect? And yeah, it turns out that you can. So like, and here I steal this figure from this paper, and this paper was one of the first who discussed this effect, and they introduced this name of spin Zebec effect. And the idea there is quite simple. So like you have, you cool one side, and then you heat up another side, and that would generate a difference in chemical potential between spin up and spin down. And then you could read this out using, say, inverse spin Hall effect. And it's important to notice, so like that the spin Zebec effect is actually fundamentally different from the Zebec effect that just depends on spin, because like it might have some different nature. And that's why it's like you stop discussing it just like as like using the language of charge. You quite often just discuss it using temperature of magnons, for example. And recently, like, so that was, I think, one of the first papers where they discussed it. And then because like the advances in measuring the difference in spins were quite amazing, they boosted the field and they started to call spin collaborators. So you want to have something with spintronics and then color that refers to the heat or the temperature difference or just the temperature. All right, and then yeah, like it was so 13 years ago or so after this discovery, like it was a quite big interest in this field, and then like they had only not spin Zebec effect, spin Peltier effect, and so forth. And then yeah, like you could find the discussion about all this in those reviews if you're interested. And all right, so like that so far it was just motivation. So I'm not really going to talk about these complicated materials like that they use to like measure and to generate this effect. So my question is actually much simpler. So like, could we just steal some of the ideas from this condensed matter background and study like with ultra cold atoms? I mean, okay, so one could have like an idea that that might be useful to understand some questions that are left in spin collaborators. It might be just, or one could just say, oh, it's just interesting. And we were not the first one actually to ask this question. So but there are very few papers. So like one could see these 2 papers if one wants to know a bit more. And our setup is quite different from what has been done. And just to bring these ideas from spin collaborators to ultra cold atoms, one kind of need like a toy model that just to get some understanding of what is going on. And this talk is about such an understanding. So like, I hope like that you will get some idea. So, and that's a toy microscopic model. All right. Yes. So what I wanted to here, I just want to say like a sketch of a system that you might have in mind for this talk. And yeah, that's very sketchy. So like sometimes I'm using actually a bit different idea. So like, please ask and interrupt if something is not clear. So like the idea here, again, it's somehow stolen from the solid state physics. So like you have 2 reservoirs that are at different temperatures, and they are connected by one-dimensional link. And then you, at time 0, you flip a spin in the middle, and then you would like to see if the spin goes to the left or to the right. All right, so that is basically what I would like to discuss. And for this talk, reservoirs actually play no role, or like they play very little role that I will discuss later on. So like the important bit is actually this, like what is in the middle. So like this one-dimensional link that has somehow temperature difference inside. All right, so again, I will reiterate what I have just said. So yeah, I would like to study one-dimensional system. And I'm in principle, I'm coming from few body physics background. So I have always a few body system in mind, which might be, yeah, I don't know, 15, 20, whatever size. And what I rarely think of a very large system. And like in this talk, at least. All right, so like what is shown here? So majority particles, why do I think that this system is one of the simplest one? So majority particles here provide a sense of temperature. So you do need them, of course. And the impurity, you introduce impurity basically to define a spin current. So without like, without another spin, you could just say that there's no spin current. And of course, you also need some interactions between spin up and spin down, because otherwise how this green particle will know about the temperature of the red ones. All right, so that's basically the minimal model that you could have. And like, what do we assume? So we assume that the interaction is strong. So, and we do that to separate spin current from the charge current. Basically, I will explain, like, yeah, during the talk what that means. And we assume box trap. So like it's really just a box trap. And okay, I say it for simplicity, but there is also a good reason to do that. Okay, and the first thing that I want to discuss is basically the zero temperature limit. So yeah, so imagine this system. I don't know how to approach that, to be honest. And then, yeah, the first thing to start would be just to go with a zero temperature. And that's what I start with. All right, so I will just write a bit more formal way, because now I understand that if I would like to talk about the zero temperature limit, I could just write down the Hamiltonian and study, for example, the ground state or just the spectrum. Okay, so that is my Hamiltonian. I mean, it's quite standard. I will just walk you through very briefly. So I have majority, say, particles and minority particles. And here, yeah, for the sake of discussion, I don't really say that I have only one impurity. I might have a few, because actually the discussion in this section is general. And then majority and minority, they interact with some parameters, say G. That's a zero range interaction, which is well defined here. Yeah, so like one body Hamiltonian just standardly has a kinetic energy part and potential, which, as I said, is a box potential. Okay, so what do we want to do? So we want to take a system that is described by such a Hamiltonian, then flip a particle in the middle, and then see how it propagates. And it's natural to ask how to do that. And right, so here, basically the method, it's pictorial. I will become a bit more technical on the next slide, but here just a pictorial idea what is going on. So I told you that we would like to have strong interactions because they decouple spin and charge dynamics. And that basically means that we map the system onto a spin chain. All right, so I'll just explain what does it mean. So at time zero, I told you, like, we flip a particle in the middle, and then like a bit later on, like we just look at the system and see where it is. And then because the interaction is strong, the only thing that could happen like this, these two particles can exchange their positions. It's remember, that's 1D, so particles need to go through each other to exchange their positions. And then when the interaction is strong, then it's rather a rare event. And then like it can stay in the middle and it could hop to the next one. But what cannot happen, like this particle cannot like suddenly be two sides away from the middle, because it's like it just does not have enough time. So like it needs first to exchange the position with its neighbor, and then change the position with another neighbor. And this dynamics is actually very similar to like to a standard spin chain that we all know and love. And it looks like that. So another way to think about it is just to say that majority particles, they create an effective lattice for an impurity. So like you could say that like, and then each basically side that is a lattice side, which is felt by the impurity. And this idea has been exercised like in a few publications, and here was a very nice experimental realization. All right. So now I will just become a little bit more technical and just tell you what does it mean, or like how to calculate this this mapping, how to establish it a bit more rigorously. So when the particles are impenetrable, so like when G is like this parameter G, which defines the interaction, is very, very large, and particles really cannot exchange their position, the system Fermionizes, which basically means that each ordinal of the particles is like an ideal Fermi gas, because that is the only boundary conditions that you have for a Fermi gas, that particles, when they are close to each other, the wave function should vanish. And that is very similar like to what Mario and Gerardo told us like many years ago. Like in that paper, he discussed bosons, but in principle, it doesn't matter. Like it can be like one impurity in a Fermi gas, it doesn't matter. And like once we establish that each ordering of the particles is like an ideal gas, it actually gives us like a basis for calculating the coupling coefficients that would define us how frequently they like two particles like in this picture exchange their positions. Okay. Yeah, so basically what we do, we just calculate the matrix coefficient for the particles when like one particle with the impurity is say to the left, is the impurity to the right. And then we say that this happens actually through this interaction. So when the interaction is infinitely large, that never happens, but when G is large, it does happen. Finitely large. All right, and then, yeah, we could just calculate this easily. So we say that delta function, it basically just gives us the probability for two particles to be on top of each other. And this probability we could establish from the boundary conditions that are given to us by the delta function. All right, so yeah, so this is the boundary condition. And you see that like on the left-hand side, you have the derivative. On the right-hand side, you have the wave function for two particles when they meet. And then you could just plug it in and get the coupling coefficient. All right, is that clear? I think that's pretty, yeah, you probably know that better than I do. All right, so like if you just do this calculation, then you get the wave function of spin polarized, then you get like this exchange coefficient that you need as an input for your spin chain. And it will be this integral. Here, like an interesting thing happens. So like you have, it basically contains two parts. So first it will be like 1/g interaction outside. And then the rest will just depend on the shape of the potential through the wave function of spin polarized fermions. Okay, so that is important. So basically you have like one bit that knows just about the shape of the external potential, and the interaction strength here is a factor. Okay. And yeah, okay, so the coupling coefficients, they depend on the shape of the trapping potential. So like one could use that to think of of how to design a proper and homogeneous spin chain, say, but it's not actually the topic of my talk. I just want to refer to these papers and mention the related experiment when this mapping, where this mapping was used to quantify the experiment. Okay, so now like an interesting part that it came to us a little bit as a surprise. So like if you have a box potential, even though the density in principle is inhomogeneous, so the wave function is inhomogeneous, the coupling coefficients are site independent. So like all these J's, JJ's, all right, they do not depend on this small j. And first we saw this like basically just numerically. So we calculated this integral, and so we saw that they are independent of like they're all identical. And then we saw there was a related paper that showed this using the beta ansatz. So you calculate, you go through the beta ansatz like in the limit when G is very large, and then you see that you could map it onto the spin chain which is homogeneous. All right, let me see what let me just summarize what I told you so far. So like you start with the Hamiltonian, which was nice and continuous. Okay, and then you map it onto the onto a spin chain, which is just XXX spin chain, and then you have some coefficient in front, which it has two parts, 1/g, and then this bit is just like geometric. And this, you could show that like this alpha A, it depends only on the energy of the state. So yeah, so you could just establish this mapping. And I have here like this subscript capital A, which basically, I have it because what I want to say is like, I talked so far about the ground state only. Or like, at least I convinced you that I would like to talk about the ground state. But what I never really used properties of the ground state. So it basically, like there are different manifolds. So when G is infinite, then I told you that the wave function is a function of ideal Fermi gas. And then like a function of ideal, the spectrum of the ideal Fermi gas will be like discrete. It will give you many states. And each state here will produce its own spin wave.
Wait, just to specify, you use G for the interaction between up and down particles.
Exactly.
You need large G because you have external potential, right? Because
no.
I don't understand then this statement, because if you have no external potential, say you are on periodic, but I'm pretty sure that hard wall potential is also working, then you can, of course, solve this problem at any G. This is what's called for fermionic Young-Gaden model.
Right. No, that is true. Yeah, okay. So that is correct.
Then why do you need large G? This spin.
Yeah, no, exactly. Yeah, exactly. So
what do you want?
You are right. You are correct. You're absolutely correct. So this Hamiltonian in a box trap can be solved analytically for any value, right? And then, like what I just told you, it applies mainly to, like we designed this method to talk about like an harmonic trap or like just an external trap.
In harmonic trap, you can't solve it if G is arbitrary. I'm not sure that even your 1 over G correction is correct. If you have external harmonic trap, one should really think carefully whether you took into account all necessary terms.
Yeah, you're correct. So like, but yeah, we thought very carefully, and we included all corrections, and then you could still map it onto the spin chain. But the difference now will be that this, a coefficient alpha is not outside, but actually it's inside. So it depends on the side.
Yes. Okay. And but then alpha depends on external potential, right?
Exactly. Yes.
Okay. Yeah. Then so just to say that second line is written as if there is no external potential.
Yeah. No, you're absolutely correct. Yeah. So like this one is in the assumption that there's a box potential. Yeah.
Can I ask a related question?
Sure.
Imagine you don't have any potential, or if you like, have a box potential, periodic conditions, but you have different methods for spin up and spin down particles. Is your mapping still working in this case?
That's an excellent question. So like, yeah, first of all, yeah, when the masses are different, then you can you still hear me?
Yeah, I do hear you.
Okay. Because I think that I'm frozen there, but all right. So the idea is like that. So if masses are different, then you cannot use this Girardot mapping to really go through and calculate these coupling coefficients exactly. So like you need this, you need to know the limit when the limit of G going to infinity to calculate this coupling coefficient. So that is how we use it. But in principle, if the masses are different, then there should be a spin chain. It's just you don't you don't know how to calculate this coupling coefficients.
I see. Yeah, thank you. It's a pity. It's a pity because otherwise it would be a very, I mean, for my own purposes, it would be very helpful to have such a mapping.
Yeah, I mean, if one could design a wave function properly, so I'm pretty sure that there are some solvable models with some mass imbalance.
No. The mix of two fermions interacting as strong Girardot with different masses is not integrable. Goodbye. Say goodbye to wave function. No way.
No, that's not like that's not exactly what I meant. So what I meant that there are some models like where even though you have mass imbalance, they are still solvable due to some symmetry of your trapping potential. So that was, I think, like first discovered or like discussed by like Maxime Olshany as so like if you have some certain Coxeter groups, then you can map it onto.
Right, but these are few body models. You don't have a thermodynamic limit there.
Absolutely, no. Like I'm not aware of any model in a thermodynamic limit where you could play this game.
Yeah, thank you.
Okay, thank you. Other questions?
So maybe you mentioned it, but I just missed it. So this mapping, I mean, this is two leading orders in 1/g.
Yes.
Like, what is the status? So there is like a term also 1/g² with some other interactions.
Exactly, right. So this method is exact. Well, it gives exact energy in the limit of the order 1/g. It doesn't even give you the wave function in the order 1/g. So like so here one needs to be careful with with the energy next order. You can't play this game because you need actually the wave function in the order 1/g. So that's basically a standard like perturbation theory argument. So that what I told you is perturbation theory, but in 1/g parameter. So we say that we do know the wave function at g equals infinity. And then using the first order perturbation theory in 1/g, we could calculate the correction to the energy by knowing the wave function only at g equals infinity.
Yeah, so it's a strong coupling expansion. But
exactly.
Then the next order 1/g², I mean, is there a systematic method to calculate like it order by order?
Yeah, I think so. Like it was discussed by Dr. Blumer, but I'm not sure how useful that is. Yeah. I never tried it.
It's as useful as perturbation theory in 1/g.
No, yeah, you're right. But like you see here, you end up with a very nice spin chain Hamiltonian that we like, and then we could analyze it and solve it. And then in the next order, it might be something not as say beautiful.
Well, it probably will involve phosphines, maybe.
Yeah, it should involve phosphines. That would be my guess. Yeah, but it's an excellent question, but I'm not aware of an answer to it.
So you are not sure if there is, I mean, if the next term can be calculated or was calculated.
So I refer to the, as I said, to the papers by Dr. Blumer. So she calculated the expansion. And I think that she did it also in 1/g².
Next, you can calculate.
Could you say it again?
I'm saying that evidently the Hamiltonian 1/g², you can calculate.
Yeah, that's something that I have not seen. Yeah, exactly.
1/g² corrections to wave function, then maybe you have trouble.
I mean, in principle, I think you can calculate like high orders because so there is a beta-handed solution for, I mean, the top Hamiltonian, and you can perform strong coupling expansion in that. And it's going to have some structure.
Yeah. No, that's of course. So it depends what he wants, because we have again this kind of misleading statement that the upper Hamiltonian is not corresponding to the second line. So we're probably talking about different things.
Yeah, that was my.
Because in the second line, alpha that doesn't depend on external potential, while in the upper line, H single particle Hamiltonians contain external potential. Second line is written assuming that the potential is both potential.
Yeah.
So that's so if you take the Hamiltonian, which is kind of periodic, then just take exactly the Young wave function expanded in G and get all terms. Enjoy.
Yeah, but I mean, my statement would be that usually it can be carried out to high order, like
explicit function. You even have explicit function. Just written.
No, but the energies are not explicit, no? Like you have to solve certain equations to get them.
No, function is explicit. It's just sum of determinants with coefficients. These coefficients depend on quasi-momentum. They to get them explicitly, you have to solve equations, but they are written explicitly.
But those equations you can solve in 1 over g. Like explicitly, you can like write a series.
Yeah, also, it's theoretical. So you, yeah, I'm not sure if you can write explicitly term number n, whatever happens. But if you ask to write down to the fixed order, you will get it. Probably. But not for external potential. Very important.
Right.
Okay. Does that answer it, or should we discuss a bit more? All right. So let's try to move on. So yeah, like this alpha coefficient, it depends only on the energy of the state. So that is actually very convenient. It will be very convenient in a few minutes. Okay, so like again, like this is a spin chain Hamiltonian that we all like, and then it is easy to solve it for one magnum. Okay, first I just wanted to say that like for this spin chain, you could easily calculate the time dynamics, and I'm showing it here. It can be done numerically or even analytically in the limit when the system is very large. So I refer to this paper. And here we show the result. Yeah, just an illustration so that you have in mind what I'm talking about. So like you start, okay, here you have 7 sides. I have 5 particles, but it's okay. So like you flip a particle in the middle. So and at time 0, you just have a particle in the middle, and then it evolves in time. And yeah, so it hits the boundary, and then it goes back. So it's a pretty understandable dynamics.
So that was the content of that paper in physics.
Could you say it again?
I'm saying that this is the essence of that paper, right? So that paper from 2005 shows us evolution of the plane wave, basically. Right?
Right. So like it's yeah. So like if you flip a particle in the middle, then you could solve it. Like you could give a very nice expression to the evolution. Yeah, of the probability.
On the thermodynamic background.
Yeah, exactly. Right. Okay, and just to give a little bit more insight into this dynamics, I will solve this. Yeah, I mean spin chain. I will show you the ground state energy of the spin chain, and yeah, that's something that you all know for a single magnum, right? And then yeah, in the limit, that's basically like referring to this comment of a plane wave. So like when p goes to 0, then you could have a very very particle-like Hamiltonian, which looks like in this time. So type, I just expanded cosine p, and then yeah, and then you could just introduce some new effective mass such that it looks exactly like yeah, a single particle. Okay, and what does it tell us? So now, if you know how like it's basically a one-body problem, like a textbook one-body problem, then you could say if you have if you initialize like some Gaussian profile, which is wide enough such that this approximation works, then it will evolve like according to this Gaussian profile. So like kind of like diffusive in imaginary time, say. Right, and then the only parameter that determines it would be effective mass. And yeah, of course, we are not the first ones to say that like a single impurity like has like this effective mass that scales, as I said, like 1 over the effective mass becomes very large when G becomes very large. So like the motion becomes very slow. Yeah, so like you could see these early papers that have very similar expression. It was just nice to arrive at from a bit different perspective. Okay. Here is a remark. Here's a remark that I want to put on the thermodynamic limit. So like one thing that we did, like when we derived all this, it was that we basically assumed a gap in the spectrum, like implicitly, because like when we discuss this perturbation theory, we kind of assume that we know the manifold exactly. And okay, it's not really a problem. Like one could come up with another derivation, but I just want you to be aware of this fact that we need kind of this gap in the spectrum for all this derivation to work. And yeah, and like another derivation might be like it might be related to the beta ansatz as what we discussed, or like another one might be just a bit physical point of view. Like you need the physics behind is just two-body scattering. And then you could try to come up with a new, you could come up with, like if it's just two-body scattering, then this coefficient J, what it tells you is how often particles exchange their positions. So it's somehow related to two-body scattering matrix. And that might be actually related, or like it might be worth trying this for mass imbalance particles if one could try to come up with a model, like a spin chain model to describe that. And yeah, I refer to this paper where this idea was exercised. All right, so now we will go to finite temperature endeavor. Are there questions regarding the previous part? Okay, then let's move on. So yeah, finite temperature, how do we do that? Okay, so we think in the following way. So like you have, and again, like here, yeah, I draw the box potential, but in principle, one could think also in more general terms, like of another potential. So like you have like ground state spin chain, and then you populate your spin, you flip spin in the ground state spin chain. And in first excited spin chain, you also flip a spin and so forth. And then you basically propagate according to each spin chain with prefactor, basically the probability of this state to be realized at T0, this state to be realized at T0. And this probability is given by basically Boltzmann factor. So what I just told you is basically the density matrix, like how we construct the density matrix. So we say that this is a density matrix. And yeah, so like we evolve. So that is, let's say at T0, where we have this, we populate this spin chains. And then we evolve, we will evolve them in time according to the Hamiltonian. And yeah, and that would be the Boltzmann factor that I talked about. And yeah, basically the temperature is 1 over beta. Yeah, beta is 1 over temperature. And that's how we basically introduce the temperature in our discussion, in our model. Okay. Right, so what next do I want to tell you? Observable, so like, yeah, so if you know like the density matrix, and then you know that the spin chains are independent, you could calculate the observable in the following way. So by the observable, yeah, I here talk about the general one-body observable, but yeah, it's easier to think about the density or the probability density. All right, so that is what you have basically if you evolve them all separately. So you would have like one observable, and it would be just a sum, like an average over all observables in different manifolds. Okay, now it's important. Like actually now it becomes clear why I use the box potential, because as I said, all box potential, they all have the same structure with one parameter outside of your spin chain, which basically means that the dynamics actually in each manifold is similar, yeah, to the dynamics in the spin chain. It's just the only difference is the time scale. So like this parameter here tells you about the time scale, And that will be the only difference between different manifolds. Let me just tell you that again. So basically what I just told you is this first line. So like the observable, it's just a sum over like this Boltzmann factor. And then there will be some function, which in principle, I don't know. It depends in principle on the observable. But what I do know is that it's the same for all manifolds. And then the only difference would be that here would be different time scale. Okay, so once we have that, we could work with that. And what we do, we say basically for low temperatures, only like a few lower states are occupied, say, and then we know that like this alpha A's, they just depend on the energy, so they grow not that quickly with a manifold number. So we could just make an expansion, assuming this alpha A is some alpha 1, and then here it would be 1 plus delta A, and delta A would be a small parameter. So if you make an expansion, then we end up with this equation, which basically, like it's we kind of exchange f. So we put the f outside, and then we change the argument. So you could just like show that that's correct. All right, but now if you actually have that, then you could come up with a new, because like this f was obtained by propagating with like your spin chain Hamiltonian for a given alpha A, so for a given A. But now this function tells us that this dynamics will be similar to the dynamics of some effective Hamiltonian with a parameter t divided by g, where alpha t is just an average over alpha A's. But it will be, again, like it will be a new spin chain, which will be now effective spin chain. So you need to be careful how you think about that. But like if you calculate the observable, say the density, then it should be similar to that one. Or like obtained from density matrix, it should be similar to the one obtained here, up to the terms delta squared, delta A squared. All right. Let me just briefly tell you how this alpha t looks. So alpha t, as I told you, alpha is basically the energy. So alpha t, that is like an energy per particle and how it behaves with temperature. All right, so now if you do the Sommerfeld expansion at small temperatures, then you get like this t squared behavior, which is kind of general for ideal Fermi gases. So you would get something of this type. And then of course, when temperature is very high, you'll have a linear increase, which is just due to classical nature then. All right, and here, like in this figure, I basically show that, how it converges with the number of particles. So for 5, 7, so it's pretty far from thermodynamic limit, but not that far, okay. And here it's a function of temperature, and I measure temperature in the units of energy per particle. All right, let's move on. All right, so again, like I told you, like that there will be the spin chain, effective spin chain, and that it will look very nicely, and then we could just again like diagonalize it, assuming a single magnon, and then we will again get this type of propagation with the effective mass, where the effective mass now will depend on temperature. So like if the temperature is high, then this mass becomes small, which is, I mean, physically, it is intuitively clear. So when the temperature is high, the particles, the colliding particles, they are energetic, and it's easier for them to exchange the position. So the dynamics, or overall dynamics, become faster, which here is basically given by the idea that the effective mass becomes smaller. All right, so that is an interesting result. And then we looked up in the literature and just to see if someone yeah, like someone discussed it. And then what we found that like in this paper by Fukuhara, that's actually an experimental paper where they measured a magnon propagation. But they also provide some time-dependent DMRG calculations at finite temperature. And they just to show, to argue that their results do not depend strongly on the temperature. So that was their logic. But like if you look at this plot, so they show normalized velocity v divided by vt, and how they define it is actually very similar to alpha t divided by alpha 1. So what I had on this slide. So it's very similar. And then if you so if you see that, you see very slow increase, which is, I mean, if you have wishful thinking, then you could imagine t squared, but yeah, I wouldn't claim that. But then they see very small increase of the order of 4% of the mass. Okay, so like here, as I said, it's actually inverse. So it shows 1/m, and then what they see here is a decrease in the mass by 4% if you increase the temperature. Okay. Again, another remark. So, and this remark is basically the same which we did before. So the spin chain was derived assuming a gap in the spectrum. So like again, we kind of always assumed that the spectrum has gaps. So that was crucial for our assumption. But of course, like you could say that if you go to very high, or like not very high temperatures, but like if you like if you populate higher excited states, then the gap between them becomes smaller and smaller and smaller. And the question would be how to understand what we actually have, how, like, is it correct or not? And basically, like besides what I showed to you, it would be nice to have another way to derive this effective Hamiltonian. So it might be by fitting to numerical simulations. So that's basically what I showed to you on the previous slide, where we see that like our results in agreement with some numerical simulations. Another way would be just to say that everything here comes from the two-body scattering. And then, again, we should say that the phonons, they are much faster. So like it's really, again, like spin dynamics that matters. And then we could derive a similar Hamiltonian. Ideally, of course, like it would be interesting to see what the beta ansatz has to say, because as we have just discussed, in principle, one could obtain this spectrum using the beta ansatz and then see what happens there. All right, so now we are going to temperature gradient. So like other questions regarding the previous part? Okay, let me move on then. And with the temperature gradient, I actually don't know how to introduce it properly. And so one needs to be careful here for sure. And then I stole the first idea. Well, I use, I shouldn't say stole. I use the first the idea that is used in this solid state physics community when they discuss different transport properties. And the idea here, like if it applies to our system, and it might be like that. Now, so you take two boxes. They are separated, so there's no really exchange between them. And then you say, I have the left-hand side is a temperature T1, and the right-hand side is a temperature T2. And then I generate particles. I basically flip spins here in the middle, which basically would mean that I flip them on the both in the both boxes. And then I would like to see how they propagate. But now we understand, so like if this is disconnected, it's a well-defined problem. It's very easy to understand that if T2, say, is higher than T1, then the particle here will move faster. And the particle here will move slower. So now if you say that I have like some constant pump in the middle, I will generate a spin current, which basically is the difference between how many particles go here and how fast, say. they go, and yeah, and then you could calculate it again using the same expansion, like one body model, and you will end up with such an expression. So like it's basically the ratio of the flux in one side to the flux in the opposite side. And what is important here is, like you have this temperature difference, which is standard for this thermoelectric effect, or thermal spin effects now. And here you have this another factor. So if T1 actually is 0, then you will have this T squared. So like it would actually be square in temperature. So if one reservoir is strictly at 0 temperature. All right, and the same, like, okay, so like here, I have them disconnected, but if you just connect them, so you allow one particle to hop here and one particle to hop there, so like you basically introduce this term by hand in your Hamiltonian, then you will have the same dynamics, because like the particle, okay, sorry, I will return to the same slide. So the particle which is at T2 will propagate faster. So it will leave this region of hopping to the reservoir with T1 faster. So that will lead to the overall spin current.
Have little time, but I still want to ask a question. I don't understand your picture. You start from quench. So when you are talking about positions of the particles, means that you are not considering them at thermal equilibrium with the environment. So it's something which you artificially insert in a form of some narrow wave packet and keep it like that until the T equal to 0. Then you basically start to evolve, right? Because otherwise this picture with the wall and two particles is meaningless, because this particle starts to run, equilibrate, and all. I mean, there is no mean of the one which goes faster than another to the right.
Yeah, like in this sense, they are in equilibrium. So like I always assume that like my charge sector is at equilibrium, which equilibrates actually fast in comparison to the spin dynamics, which is slow, because this 1 over g parameter is very large.
So you are again telling us that you have a cold gas, right, fluctuating lattice of the charge, and on top of that you create a special state, a single spin flip, and then you say, okay, it goes, right?
Yes, exactly.
No, okay.
Here I do rely heavily on the idea that like my spin dynamics is slow. It can be as slow as I wish, and my charge dynamics, my equilibration is fast, which is it's basically given by K Fermi. Speed of
in a way, then I don't understand why do we need two particles, because it's just a propagation of a boundary. If you would take one and let it go, it would be probably the same.
Exactly. Exactly. You're absolutely correct. So here, I basically just say that it's just two separate reservoirs. They do not talk to each other. But exactly like on this slide, what I show is exactly what you are saying. So I take one, and then it in the middle. And then I allow coupling now between the two regions, and I allow the particle to run. And that's exactly what you said just, right?
Probably. Yeah.
Okay. Thank you for the question. Yeah. All right. So again, like without gradient, that's what we discussed. So like without gradient here, I mean T1 equals 2 T2. So that is without gradient. And then it's what we saw already. But with gradient, then we see like the particle moves faster to one side than to the other side. And the reason for that is like because the mass here is smaller. So you could say the mass here is smaller, so the dynamics here is faster. So just like it gets sucked into the hot region. All right, so I don't have that much time left, so I will just briefly say that in principle, one could include reservoirs using density metrics like Lindblad master equation. So one could do something like that. And then like one could even introduce a spin pump in the middle, and then like one could study steady state. So like so far I told you just about some time dynamics, but in principle, what we want to have a steady state, and then we want to study like in a steady state, and we could introduce all the standard like coefficients for the heat transfer, not heat, like spin transfer and so forth. So that's what one would do. Then one would have spin pump in the middle, and then one would have like some reservoirs at the sides, get like some sort of steady state, basically like what is done in the normal Zebec effect. And then one would analyze the steady state. Right. Okay, so I think that like I will just summarize. Right. So if the only thing that I want you to remember from this talk is that like without gradient, so yeah, the particle, there's nothing breaks parity. So like a particle can move to the left, to the right, or to the left, doesn't matter. Of course, like if you introduce now temperature gradient, yeah, you break this parity, and the particle will get sucked into the system with hot reservoir. Okay, so that is basically the summary. And I would like to thank my collaborators, Rafael, who was in Atlanta, but now is in Brazil, Angela, and Nikolai from Denmark. Yeah, so I would like to thank them for this collaboration, and I would like to thank you for listening, and thank you.
So if you want to compare your effective theory with or make any predictions about the actual motion of the impurity in real space, how are the lattice sites that you introduce related to the spatial position of the impurity?
Oh, that's an excellent question. Yeah, so it's not, yeah, so like here, I will just find some, probably will go to the very beginning, and I will, yeah, so like here. Like the question is about like, yeah, so the particle moves, and then we map it onto like a spin chain, and basically we lose all information about the spatial movement, but we have only some information about like if you really just like look at our experiment, like in our lab, and then we say how many particles are to the left and to the right from the impurity, that's how we kind of can map it onto a spin chain. So in this way, the information about the space is pretty much gone, and you could understand it even in the following way, that like if, for example, G is infinite, then like this particle in the middle, it still can move a little bit, but in our language, it will be only in the middle, say, because it cannot exchange position. You could make some statements only about some average motion. So like you could make, yeah, like that's something that you could do, like average motion where you, for example, if you look at a few sites already, like at large length scale, then you could say what is the probability to find a particle there. That's something that you could do. But for example, like yeah, like this logarithmic yeah, behavior that was discussed also during this conference cannot be obtained here.
Okay, so right, so in a sense, the sense of space is lost in this mapping. And when you make predictions about how the impurity travels along this fictitious auxiliary lattice, you probably need to, for example, to take into account the Galilean invariance of the system, the currents that are created by the heat gradient or temperature gradient, to try and interpret your results in terms of the actual observable effects. Because if currents are created, if background currents are created in your system, then you need to do a Galilean transform to interpret the motion of an impurity on lattice in some spatial terms.
Exactly.
Right? So, yeah. So that.
Right.
Yeah.
So like, it's a very good point that, like, for example, like if we create here and like, in this reservoir, like say we create here temperature T2 and here temperature T1, then in principle, like, there will be a current, real current.
Wiedemann-Franz current. Yeah.
Yeah. And then, like, so if you are in solid state setting, then you could really say that there will be some steady state because these reservoirs are infinitely large. But if you're in cold atom systems, then of course that's not what would happen. And that's what, like, for example, these experiments are also inspired. This graph is also inspired by the experiments of Tillman-Esslinger. Then of course, like, there will be current to one side, but because you have finite number of particles, there will be current to another side. So you need to be careful. And what you said should definitely be included if you want to compare to real experiment. Yeah.
Right.
But there are some other ideas for if you how to do that, but I am not presenting it here.
Okay. Thank you.
Thank you.
Yeah, so when you showed this formula with temperatures, you know, this T1 minus T2, T1 plus T2, this formula is this is classical, right? So temperature is just the kinetic energy of the impurities, kind of related to that, right? Do I understand correctly?
Yes, exactly.
But does it take into account that, okay, the temperature should be smaller than the band, right? The spin band or not? Or is it on, you have to be on the bottom of the band?
What do you mean by the band?
You have this spin band, right? Of the width of 1/g or something like this.
Okay, yeah, like that's an excellent point. So, and there are two things that I want to comment. Like first thing, like that, like in our like spin chain. So like so like if you talk about like a normal spin chain in a solid state physics, then of course like you talk like here we really fix that we have only one impurity, so we don't have spin flip. We don't have spin flip processes. So like for example in solid state physics, you would say that like there are possible process that flip spin, and then that's something that is not in this theory in principle. Now, like regarding like this question about the temperature, and then I think that what you refer to is you refer to this graph, right? So when so we have to say that the ground state, then you have a gap, and here you have the second part. Do I understand your question right?
Actually, yeah, I'm sorry. So I didn't understand what means the first excited state.
All right.
Because the pictures show the same.
Like this picture?
On the left, these pictures are absolutely identical.
Okay, yeah, so sorry for that. Yeah, so the idea is like that. So like say you are exactly at G equals infinity.
Yes.
And then your gas is basically a gas of spinless fermions. Like, or you could think of it as about a gas of spinless fermions.
Yes.
And then like, the ground state of spinless fermions is basically when you just occupy everything to the Fermi level. And then the first excited state, that would be when you promote one particle, you create one hole, and then that would be one particle, and so forth.
Okay, fine. So my question is now, so now you have two energy scales. So you have this gap between the ground and first excited, this like charge, right? Charge excitation. And then you have very small width there, which is of the order of 1/g, which is the spin. So these temperatures that you showed there, how they compare to these two quantities?
So it is a very good question. So like first, yeah, the temperature should be large in comparison to this 1/g. So that it would make sense to populate it. And you also, of course, like you want to populate many states here. So that is fine because, yeah, like the only thing that you need to be careful, again, like if you want to be technically correct, then you need to always say that like this gap is large enough for this 1/g perturbation theory to work.
Right. I see. So that formula is valid when temperature is larger than 1/g.
Yeah.
I see.
But in principle, 1/g parameter can be, I mean, in our theory, it can be as large or as small, as small as you want. So that
yeah, but then I want to come back to this, to the very definition of the model, and correct me if I'm saying nonsense. In the previous slides, you were showing us the model which was a sibling of Maguire model, basically impurity plus gas. So then you show these pictures where particles have two colors, and you show spins or arrows simultaneously with different colors. But actually, you don't need, either you use, in Maguire at least model, either you use up-down arrows or you use green-red colors.
Exactly, yeah.
Fine. So now let's come back to your picture and remove, say, whatever you want to remove, up to you, either color or arrow. But then I don't understand what you are doing, because you are telling us that you are looking at large, so G is large, and you are saying that the temperature is larger than 1/g. But if temperature is larger 1/g, then I don't understand. You're saying that charge is not fluctuating, but at the same time, then the spin sector should fluctuate, and which there is no blue or there is no this red green up down. There is, for example, no up down and I mean that say if you forget about colors, then there is no spin polarized state on the left. There is no spin polarized state on the right. When you couple to reservoir, then the number of spin up particles or spin down is not conserved. So basically, you have a fluctuating.
Excellent.
Because the spin band is much smaller than the charge band. Charge is not fluctuating, so spatially they don't jump. But in terms of spin, there is no such a state as spin polarized state, because then there is no temperature. So I don't understand actually the.
Oh, it's an excellent point, and like I had to be a bit more specific what I mean. Like, yeah, if you look at the reservoir, then like if you want to talk about the reservoir, then you would see that all particles are actually identical except one. And in this way, like it's inspired by this spin color electronics, so forth, because like then you talk only about ferromagnet. So you take a perfect, say, ferromagnetic insulator, and that is very much similar. And then you introduce one impurity. So there is no, like really, this number is conserved globally by assumption. If you had some other particles, spin down particles, say, like impurity in the reservoir, that would be a different story.
So you are talking about temperature in the charge sector, which is basically much bigger than the exchange in the spin sector.
Yes.
Between this impurity and the reservoir, and at the same time. Yeah, I understand. So the point is that the impurity can't be kind of number of, you are working in a sector with given parity up down number, and so these charges are fluctuating. But you are saying, yes, Vadim asked you don't care about these fluctuations for your picture. You are looking how on top of these big fluctuations there is a slow process of kind of spin wave propagation.
Yes.
And you are saying that, yeah, if you use on this working on this squeezed lattice, after some time, you will recognize the spin propagation on top of kind of fluctuating charged gas, which is, yeah, okay, at least I understand what you...
Exactly. And it's like, it's pretty similar. Sorry?
The spin chain is basically infinite. No, otherwise this thing would not depend on temperature. It's not infinite, it's just there is some gradient flow. Or at least very much. Yes, so the distribution of the spin momentum.
Charge momentum, spin are all up, kind of.
It's not like they all take in the bottom of the back. They are distributed from the bottom of the that is small difference.
So basically, you inserted an impurity, a strongly repulsive impurity, in the hot Fermi gas with the gradient of a temperature, and you are saying that you are looking at the propagation of the temperature in neglecting the fluctuations of the Fermi gas temperature.
Yeah, propagation of the impurity, neglecting basically heat transport and fluctuations.
And the spin and the parameters of the spin Hamiltonian there do not depend on temperature in the charge sector.
Oh, they do. They do. That's the point. That's the point. The whole talk is about, so this approximation neglects energy exchange or temperature exchange between the Fermi gas and the spin chain, which is not actually a spin chain, but just one spin in the spin chain. So there is no heat exchange between these two subsystems. The single spin propagates in the mean field approximation, which is validated by small 1 over g, because the heat exchange is going to occur in the 1 over g squared order of perturbation theory. It could be powerful, it could be quite strong, but it is neglected in this talk. So, or in this approximation. So the single spin evolves in the mean field theory, neglecting exchange of heat between the two subsystems. And this mean field theory, in this mean field theory, the parameters of the fictitious lattice depend on the local temperature of the Fermi gas. So that's the idea. Did I get it right?
Yeah, exactly. Thank you. Thank you for summarizing so nicely.
But the Hamiltonian that you wrote, I mean, for the spin chain, where is temperature there?
I mean, the Hamiltonian, of course, does not know about the temperature. I mean, the Hamiltonian is just something that you have.
You passed it. You passed Hamiltonian.
Yeah, no, but I wanted to say where I introduced the temperature. So the temperature can appear basically only in the density matrix formulation, and yeah, and that's how we do it. So
but we are talking whether your Hamiltonian depends on top temperature.
Was written for the ground state spin chain or in general.
All right. So okay, let me see. So like this effective Hamiltonian, you mean this one?
Yeah.
Yeah, this Hamiltonian is written for finite temperature. Yes. And but this is effective Hamiltonian, so you need to
And this is the temperature of the Fermi gas or whatever.
Yeah, this is the temperature of the external gas. Yeah.
And this temperature is not, there is no heat exchange between the gas and the impurity. So the impurity is not heated by this. So this is a mean field approximation. So in the mean field approximation, the exchange constant or exchange coupling is a function of the temperature of the host gas. That's the idea.
Yes, it's like one small comment on top of that is like, yeah, like talking just about the temperature of a single particle is, yeah, like one needs to be careful here. And right, but the system as a whole is thermalized, yeah, in a sense that, yeah, like if you look at
there's no Brownian, let's put it this way, there's no Brownian motion of your particle, which means that it is not in contact. So no Langevin terms in the effective description. So there are no fluctuating fields which cause.
There are no fluctuating fields, that's correct, yes.
Exactly, so that's the mean field approximation.
But, so the Brownian motion will enter in the 1/3 squared.
Indeed, yes, that's not what.
No, but correct me if I'm wrong. Now I'm again. Well, anyways, it's last talk. We can stop anytime. Correct me if I'm wrong, but then the alpha depend on L, because actually this is it's on a squeezed lattice, but when you have a temperature gradient in real space on the squeezed kind of and please, how do you do temperature gradient using the Hamiltonian, which it doesn't have temperature gradient? Yes, but it's anyway, it should depend on L. So it should enter. If it doesn't enter, then there is no gradient.
Roughly say that L is equal to X. So L is X multiplied by the average of the particle.
Then I'm buying. Okay, L is X average of the but and alpha depend on X. Alpha of T depend on X or L.
Yes.
Or well, I haven't seen how you solve it. So anyway, so I think if you took this into account from anybody's side.
If your alpha depends on temperature, temperature depends on alpha is the band width basically, right? Or if you want effective 1/effective mass. Yes. No, it just so temperature changes in space, and your impurity then will search for higher temperature because there its energy is lower, kind of.
Yeah, I mean, exactly. That's basically the whole point of my talk, that like, yeah, like when temperature is high, then I mean, it's logical that like particles move faster and exchange position faster. And that is it, yeah. And this idea that like particle exchange position faster, I formalize it here in this way, but as I said, like there are also indications from DMRG calculations and so forth. Right, but I think that the idea is quite logical.
Okay, so then I completely misunderstood your kind of talk. Got it? Okay, fine.
Yeah, sorry for misguiding you.
Yeah. Okay, yeah. So that's the picture. But again, if you can show us the simulation, Dimo, you always have a right and left running wave, because even if you would have no gradient of temperature, if you start from impurities from the center, they will a half will write to the so actually the temperature gradient is related to the net difference of right wave and left wave, right? So that's so this asymmetry means, but you shouldn't think that the impurity runs from right to left. On average, yes, but in principle, yeah. So that's.
I'm a bit confused about the extension then that you have. I mean, if that alpha depends on temperature, in this expansion, I thought it was expansion for the spectrum. You know, when you had this original model with a delta function, and then you had this effective spin model.
Yeah, let me just go there, sorry. On this one.
Yes, this one. So alpha here, what? I mean, it depends on temperature?
No, here, I was, sorry, I was probably a bit fast sometimes. So yeah, this is just a Hamiltonian that describes your system. And that is, I don't have in mind temperature. At this moment, I don't have in mind the gradient. I just solve my system. And then I map, or like to solve basically in the spin sector, I map it onto the this Hamiltonian, the spin chain Hamiltonian. And
right?
Could you say it again, sorry?
It's specific. So you start with a certain state for the tones in the tones needed.
Yes.
Alpha depends on the state.
Yeah.
Yes, exactly. Mm-hmm.
But it does not depend on temperature.
Here, in principle, yeah, it doesn't, because the temperature does not enter. But you could think that like it will like appear at later on, because this alpha is different for every state, and temperature basically will just tell you that like how many states with a certain alpha participating. And yeah, that's how you get like this average.
So then you average at some point. I mean, this thing over like with Boltzmann distribution.
Yes, exactly. Yeah, so like here, so like you start here, like you propagate in every Hamiltonian separately, and right, then you say the time scale is the same, so like they're all kind of identical, and then yeah, and then you arrive at this this idea that this function, like the observable, is just a function which depends on t multiplied by the average value of alpha. That's where you average over alpha A.
Okay. Okay. Yeah. And now it's more or less clear.
Thank you.
Okay, yeah, maybe even on this quiz state, what this Emmanuel Bloch did on this quantum microscope, right, where they looked at this imagery in real. So you can really image the positions of spins, not in space, but you just remove the variations of distance, and you just plot kind of numbers, particle number 1, 2, 3, 5, and then you kind of removed spatial fluctuations. You are saying that I'm just looking whether kind of particle number 5 has which color it has.
Exactly. Yeah. So I had this idea.
Yeah. So you can.
And that is in this paper. So if someone is interested.
I'm not. It's no. It's theoretical with Jamarki, but there is this paper with Emmanuel Bloch and I think Demler in
I think that is an experimental paper.
Ah, this is experimental. So this guy is because Jamarki then wrote in. Okay, I see. Yeah, I probably.
And they have they have this discussion on temperature, just kind of to validate, because like the temperature is not small, or like, okay, it's small, but it's not 0. And they wanted to estimate what is the effect on this mass, because that's what basically they measured. It measured the mass, and they saw that actually it agrees very well with the 0 range, 0 temperature result. And then they did DMRGT calculations, and then they saw that the variation is very slow. And within our approach, you can understand that it's slow because it increases or decreases the mass as t squared is actually a pretty large prefactor. And that's why you don't see anything.
This is the paper which just has entitled spin charge separation something, right?
It might be a microscopic observation. Yeah.
Of spin charge separation in equal infinite U. Yeah, because there are, okay, then they just published more than one paper, that doesn't matter. Okay, thanks. Anyways, sorry guys.
Thank you for the comment.
Anybody want to ask anything else? Okay. In such a case, we thank the speakers. This was the final talk of the workshop. And well, those who survived our workshop or who attended it, thank you everybody. The talks will be on YouTube. Please don't forget, send me your slides. Please don't forget. And I stop recording.